Hi everyone and welcome to this lecture. So in the previous lecture we discussed what are differential equations, and from today on we will try to see how we can solve different kind of differential equations. And today we are going to talk about separable equations, that is first order ordinary differential equation, and among them there is a particular class called separable equations. So a separable equation has the following format. Let's say there is some y which is a function of x, and you will have a differential equation in this format. So this is the format of a separable equation. That is, the reason they're called separable because you can see that on the left hand side there is a derivative, because we mentioned that differential equations will involve derivative of functions or functions. That is, there might be one function, there might be many functions, but it will always involve a derivative. So left hand side is kind of done, but the reason they're called separable is actually coming from this part, this f of x and g of y, because it has two functions. One of them is a function of x, that is f, and this g function is a function of y, and they are not intertwined because g is purely a function of y. So g of y could be, let's say, y square, y cube, whatever, but it only depends on y but not on x. And similarly we can say the same for f of x. It's dependent on, let's say, just x cube, it might be x to the power 34 or and so on. And from there, that is from, let's call this equation 1, you can see that you can easily decompose this equation 1 in this way. So what is happening over here is that at one side you only have to integrate over y, and on the other side you have to integrate over x. So that's why they are called separable. And after this line we can try to solve this, because you can see that at this line, this is just, let me just write it again. So this is just dy by gy, and this is f of x dx, right? From our ordinary calculus course we know these things. And after that, what you need to do, you need to integrate on both sides. But on the left side you are integrating over y, and on the right side you are integrating over x. So as you can see, I'm not writing any integration limits right now, and instead of doing that I will take an arbitrary constant. So just integrate on both sides, and this can be denoted, because this is a function of y, this g of y is a function of y, and if you integrate with respect to y you will get some function of y as well. For example, if you had dy by y and you integrate it, this is just ln of y, right, plus some arbitrary constant. So let's call this function, whatever the thing might be that is coming from integrating 1 upon gy, let's call it g of y, and let's call our arbitrary constant as c1. And on the right hand side we'll call this integration of f of x dx, that when you integrate it, let's say this is giving us some function capital F of x, and here is another constant, let's say c2, right? And now we can simplify these things a bit more, taking this c1 over to c2. So let's write g of y is equals to f of x plus c2 minus c1. But this linear combination of this constant will also give us a constant. So finally you can write the solution, the most general form of this solution that is coming from a separable equation, as like this, where c is arbitrary constant that is determined by the initial or the boundary conditions, and this g of y and this f of x will come from integration. So now we are done with the theory. Let's see some examples. We'll take one example and it will be a bit lengthy, so that we can understand how to use the boundary or the initial conditions. So the problem we'll consider right now is the initial value problem, but most of the time you actually don't need to worry about what is the initial value or what is the boundary value. So just keep in mind that those initial values or boundary values only will play a role for determining this arbitrary constant, nothing else. So let's call our equation as the following, that we want to find dy y as a function of x, but our equation, that is the differential equation, is dy by dx is equals to 4x e to the power y minus 2x, and the condition when x equals to 0, y will be 0 as well. So this is a very easy integration, as you can see, that I can easily separate my parts, that is parts depending on x and parts depending on y. So if you do it like this, you can see that there is a 4x e to the power y times e to the power minus 2x, right? Now let's separate them. So this will be dy by e to the power y, and I'll have 4x e to the power minus 2x and dx over here. And now you integrate both sides. Again, we are doing indefinite integration. So if you do it like this, then you will have minus e to the power minus y. That's the integration coming from this part. And here you will have, first you can integrate e to the power minus 2x, and then you can use integration by parts. So if you do that, I'll just write down the whole result. That will be 2x plus 1 e to the power minus 2x plus c. So this is a g of y, right? And this looks like a capital F of x, and this is our constant, just like we mentioned here before. And now what we want to do, we want to use this piece of information over here to find out what is c. So notice, when x equals to 0, y of 0, that is y, is also 0. So first you need to put x equals to 0. So put x equals to 0 and y equals to 0, because y of x is equals to y of 0 is equals to 0. So if you do that, you can find that this part over here, this will be just minus 1. Here, if you put a 0 over here and a 0 over here, you will get also a 1, and there is c. So c will be minus 2. And if you just plug it back, you have your particular solution. So one thing I didn't mention is that when there is this general form where the constant is arbitrary, this is called a GS, or a general solution. And a particular solution is that whenever you have a value like this for this arbitrary constants, that is, the arbitrariness is not there anymore, that is called a particular solution. So graphically, let me just try to give an idea what I'm talking about. So let's say I have some function y of x is such that x square plus c, like this, or just x plus c. So you can easily see that this will be some, due to some arbitrary constant, that is c. Let's say when c equals to 0, this line goes through the origin. When c is equals to 1, it will cut some line like this. So you will have a lot of solutions. And let's say this corresponds to c is equals to 5. I'm just taking these things arbitrary. We don't need to be accurately 100% accurate over here. So these things are called family of solutions. But now if you fix c equals to 0, if you fix that, so you are just picking out this line, I'm marking with red, this line that corresponds to c equals to 0 among all these lines, that is all the straight lines you can have for different kind of c's. You are just picking out this one particular line, this one. This is your particular solution. So this is how you can easily do the separable equations. They are pretty easy to do because the integration gets decoupled. And if you have some initial or boundary value conditions, then you can obviously find out the particular solution as well. So this will be it for today, and I'll see you guys on the next lecture. Thank you.